Good morning to all the participants at different nodal centers. So we are going to start with our first technical session on VLSI overview. So myself, Dr. Rajesh Mehra, and I am going to take this session on VLSI overview. First of all, outline of this complete session are introduction. Then we are going to discuss design options available with us for VLSI design. Then what is the design flow that you have to follow for your particular design. Then classification of your design, whether you are going to work on front end VLSI design or back end VLSI design. So after discussing all different aspects of VLSI design, we are going to conclude our session and then some references for this whole presentation. So first of all, introduction. Actually, whenever we talk about VLSI design, then we normally work in any one of the three domains. There are three domains, and these three domains are your behavioral domain, structural domain, and physical domain. Behavioral domain is basically your graphical kind of representation, textual kind of representation, where you write your code for your particular design, and then you simulate your code and you check the behavior of your complete design. In structural design, we follow graphical representation. It is just like you can say schematic diagram of your complete design. You design your circuit and then you simulate it and you check the logic functionality of your design. Then physical domain is basically you create different masks, different layouts for creation of your chip. And it is at transistor level. You create your own transistors, or sometimes you work on semi-custom designs, and in this way you design your own chip. So directly or indirectly, you start working in any one of these three domains depending upon your convenience and the kind of input you have with you, and based on that you design start your design. These domains can be divided in different hierarchical levels, like it can be architectural level, then from architectural level to it is register transfer level. A register transfer level is basically you are going to use some kind of modules. Then logic level means you are going to design your circuit in the form of gates. Then circuit level, basically you have your circuit in the form of transistors and you start your design in the form of transistors. And these are three different domains. Here you can see that, and in these three domains we can just see whether you want to work in behavioral domain or you want to work in structural domain or physical domain. And selection of these domains depends upon the input you have. Means if you want to you are working in on some kind of paper, then the circuit present in that paper, if it is in the form of codes, then no doubt you have to select behavioral domain. And if it is in the form of logic gates, then you have to select structural domain. And if it is in the form of transistors, again you have to select structural domain. And if it is a chip level design, then you have to go for physical domain. So depending upon these three different domains, different vendors, they have provided different softwares, and each and every software supports designing in each of these three domains. So whenever you select any software, it should be compatible with all these three domains so that you can start your design in any one of these domains. So when we say a VLSI design, a good VLSI designer, he or she takes care of different parameters related to VLSI design, and those different parameters are related to performance of your design, and performance can be checked with the help of different parameters like your speed of design, then how much power is consumed by your design. And speed is very important parameter for real kind of applications. If you want to process your signal coming from environment, and you are going to take that signal, you have to process it, and you have to give response in very short time. In that case, that speed matters, and power is very important if you are basically system which is you can say battery operated or portable kind of devices you want to design, and in that case power consumption is very important factor. Just like your mobile phones, if you can design a system that consumes low power, then your battery is going to give you the lifetime of your battery will be more. And functionality is major concern. Your system, it should work as per your requirement or as per your logic. So functionality of your system, it should be very correct. And flexibility here means that your system, it should be flexible in nature. You can say that if you want to modify something in your system, that modification should be possible, and it will be possible only when your system is flexible in nature. So apart from all these things, you take care of performance by optimizing all these parameters. You have to take care of cost of your system also. If you are designing a system and it is perfectly all right in all the performance parameters, and if its cost is very high, even then you cannot survive in the market. You have to provide the solution, or you have to provide the optimized solution, so that cost of your overall system is very less. So you have to compete in the market, and your system should be less costly. And the third and very important factor is time to market factor. Whenever you design something, when you design some product, you have to design that product in a very less time, so that you will be able to launch that product in the market in a very short time. For example, if you are working on some product and you are providing better performance, your system is also low cost, but in between, if some other vendor, they launch their products which is similar to your product, and performance is compatible, and it's their cost is also comparable with your product, then it will be very difficult for your product to survive in the market. So time to market factor is very important. You have to give the solution in a very short time. You have to take care of performance of the system, and you have to take care of the cost of the system. So these are some parameters you have to take care in your mind whenever you are designing any product. So these are very important factor for VLSI design. And different options for designing your systems are, if you want to work on ASICs, ASIC here stands for application specific integrated circuits. If you want to design any chip, you can say, and that chip should be application specific, then we have different softwares available with us, and you can choose any one of these softwares, and it is possible that one of these software is already there in your institute, and you can start work on that software. And most important softwares are Cadence. They provide very good backend, you can say, solution. Synopsys is there, Mentor Graphics is there. These three are important, you can say, industry standard tools, and you can design your chips, and you can create your chips also, and you can implement them in actual environment. Apart from these three softwares, we have two more, not two, more than these. Number of softwares are available in the market. I am just giving you example of some of these softwares. And then Microwind is one software, and Tanner is another software. They are also good for lab practices. You can give complete exposure, or you can say complete design flow to your students by using these softwares. So basically, you can say that if you want to design ASIC, then any one of these softwares should be there with you if you want to work in this area. Then the second part is programmable logic devices. Programmable logic devices available these days are your CPLDs, your FPGAs. And CPLD here stands for complex programmable logic device, and FPGA stands for field programmable gate arrays. And in if you can say that if you design ASIC, you are basically creating your own chip. If we are using PLD, then we are programming an existing chip. That existing chip can be CPLD or it can be FPGA. Now you have to program your chip according to your requirement, according to your design specifications. And for programming of these CPLDs and FPGAs, you need some kind of software. And in that case, Xilinx ISC, they are providing solution for programming and these CPLDs and FPGAs. Apart from this Xilinx ISC, other vendors are also there, like Altera is there at present. Intel, they have collaborated with Altera, and they are providing solutions for FPGAs, and you can use their softwares also for programming these programmable logic devices. So these different options are there depending upon the input with you. You can select any one of these options and you can go ahead with your design. Now, once you go ahead with your design, then you have to follow some design strategies. First of all, you should have design specifications. Whenever we start our design, we should have something in our hand so that we can go ahead with our design part. Maybe if you are doing some kind of research, then you have some paper with you, and in that paper you have some design specifications. Based on those design specifications, you have to start your work. For example, if you are working in some kind of standards, you are working on GSM, you are working on 3G, 4G, 5G these days. So all these different standards, they have different design specifications. So you should have good idea about these design specifications. Only then you can go ahead with your design part. So first very important part in your design flow is design specifications. You have to collect data and you have to collect the information about the design specifications. Once design specifications are there, then you have to write down its code. As I told you, there are two domains, behavioral domain and structural domain. Behavioral domain is used for code writing. Structural domain is used for schematic design. Code writing means you are going to write your code in textual form, and your structural means you are going to design your system in graphical form, and that will be your schematic design. If you compare these two designs, writing code is you can say it is flexible kind of thing. You can perform modification in your design if you write your code. Modification is easy if you are proceeding with code development. If you are using structural domain, in that case, structural domain is easy to understand, but it is difficult to modify, right? So whenever we go ahead with any kind of research, then flexibility should be there with the designer. Your code should be flexible. You should be able to make some changes in your design, and that thing is possible with the help of code development. Both the options are there. If you are going for research design, then it is always preferable to go with code development. Then synthesis and simulation. Here synthesis basically, once your code is developed, then you synthesize your code. Synthesize your code, basically it gives you information about the number of resources, about the performance of your system, means how much resources are used by your design. And after optimization, it also includes optimization of your complete system design. And this part we are going to discuss in our tomorrow's session, logic synthesis. There we are going to discuss it in you can say more detail. Synthesis here means you are going to calculate the resources required to design your system. Along with this, it is also going to give you information about the speed of your system. So basically, whatever those parameters are there, performance parameters, those will be you can say calculated in this synthesis part. Simulation is performed here to check the behavior, you can say that, or you can say that functionality of your design. So you have to check the behavior or functionality of your design. If it is as per your logic, or if it is as per your requirement, then only then you can move ahead. Otherwise, first of all, you have to make changes in your code. You have to again simulate it. You have to check the behavior. You have to check the functionality. If it is as per your requirement, only then you will go for next part. Then comes your placement and routing. So once your resources are defined or finalized, you can say that, then we place these resources on prefabricated areas. Prefabricated areas, Whenever we are dealing with PLDs, programmable logic devices, in PLDs you have CLBs, configurable logic blocks. Number of CLBs will be there, and if you are creating any semi-custom ASIC, there also you will get prefabricated resources. So out of those resources you have to select some part where your this design will be placed. So you have to select the portion where placement will be there. Once your placement is selected, means at this particular part you are going to place your design, then next thing is you have to make interconnection between placed resources, and that interconnection is known as your routing. So placement is very important part, and once your circuit is placed, you have to route that circuit, that is routing. So placement is and routing, and the final is your implementation. Implementation is once your design is placed and routed, means your now design is complete and it is ready for you can say hardware checking or hardware verification. So once your design is placed and routed, then you have to check its implementation. You are going to now check your design in hardware, whether it is working as per your requirement or it is performing the logic as desired by you. And apart from functionality, no doubt you are going to check the speed of your actual design also. So these are 5 major parts in a complete design flow. So you have to perform all these parts, and you should be very you can say specific in each and every part, so that you can make your design very reliable design. So first, system specification. I am just here taking one example of filter design. For example, if you want to make filter, as I told you, there are different standards. You can work on 3G, you can work on 4G, you can work on 5G. Whenever you are going to design some filter related to 3G, 4G, 5G, first of all, you should have some specifications. So that specification may be in the form of cutoff frequency, it may be in the form of passband frequency, stopband frequency, passband ripples, stopband attenuation. So these are different parameters, and you are going to get the specification of each and every parameter from different standards. And based on these specifications, first of all, you are going to design your filter in, let us say, MATLAB. So you are going to write your code in MATLAB. And once that code is ready, again, you are going to simulate your code in MATLAB. Once that code or your filter is performing as per your requirement, then the next thing is you have to go for synthesis part. So here, whenever you design, then you have to take care of filter order, because filter order is a very important factor in order to specify the area of your design or to specify the speed of your design. So you have to keep your filter order very minimum so that we can make your design you can say less in cost, and it should be high in speed. So after these design specifications, you have to, as I told you, you have to start your code in MATLAB, and then you are going to simulate it. And from MATLAB you will get filter order, and you will get different coefficients and value of those coefficients. Based on the value of those coefficients, you are going to develop the HDL code. This HDL code, it can be VHDL or Verilog, depending upon your convenience. If you are comfortable with VHDL, you can go ahead with VHDL code, or if you are comfortable with Verilog, then you can go ahead with Verilog code. So again, here MATLAB part will be done in your MATLAB, and you have to keep your filter order minimum possible. And HDL, here you can use ISE, or as I told you, you can use Intel or Altera softwares for VHDL and Verilog. And your design can be, it can be serial architecture, it can be parallel, it can be partially serial. Here serial architecture means this kind of architecture will be area efficient, but it will have less speed. Parallel architecture will be your high in speed, it will show better speed, but it will consume more area because you are using parallel structure. So if you want to optimize between area and speed, then you have to go for some in between solution, and that solution is your partially serial solution. Here you can take care of your area and speed, and in this case we can find out in between solution. So depending upon your architecture of your whole design, we can make our you can say HDL code uh, as per requirement of our hardware. Then the second point was simulation, and once you're here again, you are going to simulate your design at two phases. First you are going to create your M code, and you are designing your filter in M code and you are simulating it. Then MATLAB is giving you filter order and different coefficients. You are going to take those values from MATLAB. You are going to use those values in your HDL, and then you are going to develop your VHDL code or Verilog code, and again you are going to check the functionality. That is your you can simulate your designing using different softwares. ISC simulator is there. They are providing you simulation environment. Then Model Sim is also there. You can use Model Sim to simulate your design. So different options are there, and you should have knowledge about those options so that you can work on your design. So once your simulation is done, then the next part is your synthesis, and as I told you, synthesis is going to give you the idea about whether how many number of resources are required by your design, and whether your design can be accommodated in that particular FPGA that is available with you or not. If it can be accommodated in that particular FPGA, only then you can go ahead with your design. If it cannot be accommodated in that particular FPGA, then again you have to optimize your design. You have to basically reduce the area, and if you can reduce the area, and along with that you have to take care of the speed also, because sometimes you have speed constraints and you have to meet those speed constraints. As I told you, we can reduce the area consumption by using partially serial kind of architecture, but partially serial kind of architecture, speed of your system will be reduced as compared to parallel. So we can say that fully serial design, area efficient, but speed will be less. Parallel design, it will be speed efficient, but area will be more. Partially serial will be you can get optimized speed, and you will get in between resource consumption. So depending upon that, you can select the resources. Then once these resources are decided, then we select particular area for placement of those resources. If we are dealing in ASICs, then you have to find out some area on your silicon, so that you can place your design on chip and you can create your ASIC. If you are dealing with PLDs, then you have to select CLBs or PLBs. Here CLB stands for configurable logic blocks, and PLB stands for programmable logic blocks. So these kind of programmable logic blocks will be available on your PLDs. So you have to place your design over these CLBs or PLBs in case of front-end VLSI design. And once your design is placed, by considering all different parameters into consideration, then the next part is you have to route your board. You have to finally make interconnection between different you can say resources used in your design. Once your routing is 100% done, that means each and every net is connected with different resources available on PLBs or silicon area, then your design is completely you can say it is done. So efficient placement and routing further optimizes. If you can place your design efficiently, it further reduces the area consumption, it reduces the power consumption, as well as it increases the speed of your design. So PAR is very important factor in your complete design. Then hardware implementation. In case of ASIC design, you have to fabricate your chip, and after fabrication you have to test your chip, and then you have to check the functionality. And this is one example of back-end VLSI design. And in case of PLDs, you program the PLD and then you test the PLD, and this kind of example is available with your front-end VLSI design. So these were different options available in complete design flow. Now we can, as our outline, in our outline we discussed that there were two major sections. In VLSI design, either you can work in front-end VLSI design or you can work in back-end VLSI design. No doubt you can't escape from PCB design also, because PCB design is also part of your VLSI design. That is why most of the vendors, they provide complete solution starting from PCB design to front-end design and back-end design. PCB design is basically used for task of PCB is it is used to provide physical placement to different components, and it is used to make interconnection, electrical interconnection between different components. So if we are working in front-end VLSI design, it means that you have some chip with you, some existing chip is there. You have to program that existing chip by using some HDL, maybe VHDL or Verilog. So in case of your back-end VLSI design, you are going to design ASIC, and in that case you have to design your circuit on silicon. In both the cases, whether you are working in front-end VLSI design or back-end VLSI design, you are dealing with chips. In first case, you have to program that chip. In second case, you have to create that chip. Once these chips are available and these are ready for you can say use, you need some kind of platform, and that platform will be provided by PCB. So we can't escape PCB. PCB is very important, you can say, part of VLSI design. So whether we are working on front-end VLSI design or back-end VLSI design, you need some kind of placement where you can physically place the components and you can make interconnection between these components. So now after PCB, we can discuss now front-end design. In front-end design, basically, we can divide it in three parts. First is HDL development, second is core gen, third is DSP tools. As I told you, in whenever we work in MATLAB, you design your filter in MATLAB. MATLAB is going to give you the order of the filter, and once that order is there and once the exact value of different coefficients is there with you, in that case, next part is now you have to go for hardware part. That is your, either you are going to use ISE or you are going to use Altera software, and in that case you have to work in HDL. That HDL can be VHDL or Verilog. Now question here is whether you are going to design your HDL at your own or you are going to take some help from some other software. If you the first section is HDL development. HDL development here means you are going to create your own code. Either you are going to create your code in VHDL or Verilog, but in that case you should have very good knowledge of VHDL and Verilog. So in this case, you are going to take the values of different coefficients. You will use these values as constant in your VHDL or Verilog code, and you are going to develop your VHDL code or Verilog code. So first, there are three parts in which you can work. Whether you can work on HDL development, you can work on core gen, you can work on DSP tools. So if you are very convenient or you are well you can say equipped, or you are very comfortable with HDL development, you will go for first option, because you will have more flexibility. You can modify your code. You can introduce more number of research components in your HDL. So in that case, you are going to create your HDL, and then you are going to check its behavioral simulation. So as I told you, you have to simulate your design at each and every section, only then you can move ahead. If behavior of your design, it is as per your requirement, as per your logic, only then you can move ahead. Otherwise, you have to again check your code. You have to make necessary changes in your code, and then you have to move for next part. So after checking the behavior, let us say behavior of your circuit is okay. Then under synthesis, we create netlist. Netlist in the sense, now your software is going to take the design in the form of textural language. As you started your code with VHDL or Verilog, now it is in the form of text. Your software is going to take this text and it is going to convert this text into RTL. RTL here stands for register transfer level. RTL means now your text, you can say that it is converted into graphical representation. You can say it is converted into schematic kind of input. Now you have graphical representation with all the nets connected with each other. So netlist is created, you can say that. So once your netlist is created, then next is, here you can see that implementation. And implementation here, it can be divided in three major parts. And these three major sections are translation, placement, and routing. Here, once your HDL is converted into RTL, RTL is your register transfer level. Now you have the number of resources, we can say that. In this portion, synthesis is done. In synthesis means optimized network is available with you with you can say less number of resources required to make your complete design, along with their internet, along with their connectivity in the form of netlist. So this information is there. So and now you have the information, means these number of gates and gates are required to make my design. These number of OR gates are required to make my design. So all this information is available with you before implementation. Now translation here means each and vendor, they provide their own libraries. And synthesis basically is divided in two major categories. Tomorrow we are going to discuss that. Here I am just going to give you a small idea so that you will be able to understand what is translation. Synthesis can be divided in two parts. One is technology independent, another is technology dependent. Technology independent synthesis means you are going to use K-map and your you can say that tabular method. We used to reduce the number of sum terms and product terms. You call them as the sum of product. And also we use different theorems, De Morgan theorems and other theorems. So this kind of optimization is known as technology independent optimization. Basically these are standard optimizations, and these optimizations are not going to change from one vendor to another vendor. These are going to remain same. Right, standard kind of optimization, it will remain same for all the vendors. That is why we call it as technology independent optimization. Second one is technology dependent optimization. Technology dependent optimization here means each and every vendor, they are going to provide you different set of libraries, and each and every library is containing some components in it, and you have to choose components from these existing libraries for implementation of your design. Right, for example, you want to use one full adder, right, and that full adder is available in library, and there are 20 options in the library. Your vendor is providing 20 options of full adder in the library, and you have to select one out of those 20 depending upon the cost and speed you will achieve by using that particular you can say full adder. So translation here means required component in your design and which component you are selecting from the existing components available in the library, right, which is optimal for implementation. So out of those 20, let us say 7 number is more optimal as compared to others. So I am going to use that 7 number full adder for implementation of my design. So that 7 number will be used for this particular full adder. This is basically is you can also say that it is library binding. We are binding different components in the library and we are binding those components with our existing required components. So this is known as your translation, right? So once translation is done, means you have selected let us say number of you need 2 full adders, you need 1 subtractor, you need 1 AND gate, you need 1 NAND gate, number of resources are required, and for all those resources you have selected optimal options from the existing library. So it means that now translation is done. All optimized components available in the library are selected. Now your task is, these components are available if I am working on PLDs. These components will be available on CLBs or PLBs, right? So I have to select, there are number of CLBs and PLBs on your FPGAs, and these components may be available on different ASICs, right? And you have to select a particular area where you want to which area you want to use for placement of that particular resource, right? So once translation is done, then you have to select particular area where you want to place your required design. So, and that placement is also very important. It is going to take care of your area consumption as well as it is going to take care of your power consumption and speed also. So it you have to use different algorithms. Each and every section basically is using different algorithms behind the software, and those algorithms are used to provide you the optimized solution. So based on those algorithms, you have to place your circuit on the PLD or on silicon area. So once your circuit is placed on the PLD or your ASIC, then the last step is you have to now make final connection between those placed components. So you have to make, and this final connection will be based on a net list. You have to make interconnection between different components, and you will be ready with your design. So in implementation, these 3 major steps are there. You have to translate, you have to place, and then you have to route your circuit, and you will get your design ready. So once your design is routed, final routing is done, then in case of FPGAs, you have to generate 1 bit stream. Actually, whenever you work on PCs, you design your code, you perform these different sections. First you perform HDL, then you synthesize it, then you implement. After implementation, you generate 1 bit file. That bit file will be in the form of zeros and ones, and this is the case for front-end VLSI design. We are talking about front-end VLSI design, and that bit file will be responsible for as we know that in FPGAs we have CLBs and we have programmable interconnects. Each bit is basically related with different programmable interconnects. In order to make your circuit on that particular chip, you have to make some of the bits 1. You have to program those bits, and if you want to program some bits, you have to make them 1. So wherever you need programming, all those bits will become 1 and rest will remain 0. So initially when you start with PLD, all the bits will be 0. It means it is not programmed. Your chip is not programmed. So once this bit file is generated, this bit file will make different required bits in that complete. Let us say there are in one PLD or FPGA, let us say there are 500 programmable points, and each point is connected with 1 bit, right? So it means there are 500 number of bits, and when you design particular system, and in that particular system designing, let us say only 45 programmable points are required to be programmed. So those 14 programmable interconnects, 45 programmable interconnects are associated with some bits in that long bit file, 500 bits. So those 45 bits in that 500 bits will become 1 and rest will remain 0, and in this way your bit file will be generated, right? And what you transfer from your PC to FPGA or CPID, you transfer this bit file only. This bit file is transferred from your PC to FPGA, and wherever your bit is 1, that particular programmable point will be programmed, it will be connected, rest will remain open, and in this way you can program your complete design, or you can say you can program your system. And once this file is transferred from your PC to FPGA, then you are ready. You are ready with its hardware implementation. Now you can check the output of your circuit in the term. You can make different changes in your inputs and outputs. Based on those changes, you can make different. You can verify the output of your circuit. So this is one complete design flow for your front-end VLSI design, and it is based on your HDL development if you are designing your code on your own. The second part is basically you are using some kind of code generator, right? ISC basically it provides one option of core gen. In core gen, you have some IP cores. You can say intellectual IP cores, in software IP cores. You can see that you can use these IP cores and you can generate the VHDL or Verilog code. In that case, there is no need to write your own code, right? So in that case, if you want to design any filter, one IP core is there for FIR filter. You can give different specifications based on your requirement. You can say generate VHDL code or Verilog code from CoreGen. So you are that part. First part is now automatically done. You don't have to write the code. Your code will be automatically generated, and it will be generated with the help of CoreGen. And the rest of the part will remain same. You have to synthesis again. Here you are going to calculate the number of resources required in your design. Then you are going to check the speed of your design, and then implementation. In implementation again, those three parts will be done. You have to translate, or we can say you have to bind the resources from the library. Then you have to place your design, you have to route your design, and finally bit file will be generated, and that bit file will be transferred from your PC to FPGA. And the third one is DSP tools. Actually, in Xilinx ISC at present, they are providing complete solution, and in this DSP tool, they are providing two softwares, and those two softwares are your system generator and Accel DSP. And Altera also providing one solution, that is DSP builders. They are also using one tool that is used for, basically the purpose of these tools is to bridge the gap between a MATLAB environment and your you can say ISC environment, or DSP builder is used again for signal processing kind of applications. So in this case, two options are there. Either you can go for system generator, or you can go for Accel DSP. As we all know that in MATLAB we have two options. Either we can work on SIMULINK, or we can work on M code. M code is your textual kind of code development, and Simulink is your graphical kind of code development. You can say that in Simulink you can create a block diagram of your overall system, and in M code you can create your own code. So depending upon the convenience of the designer, if you are more comfortable with graphical kind of designs, for example with Simulink, in that case, if you want to bridge the gap between Simulink and ISE environment, then you have to use system generator. Here, actually, the task of system generator is MATLAB gives you output in terms of floating point numbers, or you can say a floating kind of output will be provided by MATLAB, and FPGAs takes the input in the form of zeros and ones. So there is a gap. It is giving you a floating kind of output, but your FPGA is taking your data in the form of zeros and ones. So you need some kind of platform that can convert this floating kind of data in the form of zeros and ones first. So whatever, as I told you, MATLAB is going to give you one coefficient, and value of that coefficient, let us say it is 4.7. So what is your task? Your FPGA is not going to take that 4.7. You have to give input to FPGA in the form of zeros and ones. So this 4.7 is one input, and this input will be converted into its equivalent digital data in the form of zeros and ones, and you have to associate some number of bits. Let us say you are using 16 bits to convert this data from 4.7 to zeros and ones. So in these 16 bits you can use, let us say 2 bits for floating kind of data and 14 bits for fixed, or you can use 4 bits for floating and 12 for fixed kind of data. So in this way you have to convert, and this conversion is basically performed with the help of these software, system generator and your Accel DSP. So they convert this floating point data into fixed point data in the form of 0 and 1, and then they generate VHDL or Verilog code for you, right? So with the help of system generator, we can generate VHDL code or Verilog code for our model. In Simulink, we call that system as model. Extension of your file is model. And if you are working in, this is one example here, you can see that we are designing one system in the form of block diagrams. We are getting the simulation of this. This is one example of Simulink. So if you are working in Simulink, then you have to use system generator, and you have to use some blocks of system generator, and you have to incorporate those blocks here with these blocks, and then we can develop our system with the help of system generator, and then we can create VHDL and Verilog. Then second part of this is Accel DSP. As I told you, if you have designed your system in M code form, .m form, in that case you can't work with system generator. Accel DSP also perform the same function. It converts that floating point kind of output into fixed point kind of output, but it takes code as input. So if you have M code, then it will take that M code, it will convert that floating point number into fixed point. Again, you can use 16 bits for input, or you can use more number of bits for input, and then it is going to convert code, or it is going to generate code for you either in the form of VHDL or Verilog. That option is available with the designers, whether you want to go for VHDL or you want to go for Verilog, right? So these two options are there. Apart from this, Altera also providing DSP builder, and that can also be used for digital signal processing kind of applications. So here you can see that in MATLAB we are first writing M code, and once this M code is ready with us, then we simulate this M code, and we get the output in the simulated form. So again whether you are using system generator or you are using Accel DSP, once your code is once your VHDL or Verilog code is available with you, in that case, next step is again you have to what? You have to synthesize, you have to check the resources, you have to check the behavioral simulation, you have to check the speed of your design, and once synthesis is done, then you have to implement the design. Implement of design again contains those three parts: translation, placement, routing. So you have to perform that thing, and then the final step will be again your bit file generation, and that bit file generation will be used to implement the, you check the hardware implementation of your design. So in this way we can say that we can use system generator or our Accel DSP to support or to bridge the gap between your MATLAB environment as well as in your this ISE environment. So here you can see this one diagram. We have developed one system in SIMULINK, and some components are used in system generator. Here you can see that the top is your SIMULINK environment, this one, and this is our ISE environment, and there is a gap between SIMULINK environment and FPGA environment, and this gap is basically filled with the help of system generator. So we can use system generator here. Another very important you can say feature of system generator is they can give you hardware co-simulation kind of features. Hardware co-simulation here means, for example, if you have designed one filter in MATLAB and you have created VHDL or Verilog for that particular filter, as I told you, FPGA is going to take this input in the form of zeros and ones. So your input will be in the form of zeros and one, and your FPGA is going to give you the output again in the form of zeros and ones. For example, we are taking 16 bits as input and we are taking 16 bits as output. So whenever you are going to simulate your design, it will be in the form of zeros and one. It is going to be one waveform, right? So 16 waveforms will be there, and each and every waveform is representing at some particular time, it is representing either 0 or 1. So from that waveform, it will be very difficult for you to analyze whether this is the output of design filter or it is something else, right? So in order to verify that the output is of filter only, we have one option, that is hardware co-simulation option. In hardware co-simulation, basically we design our system in SIMULINK with the help of system generator, and we simulate that design using PCB, and we again develop code, and that code will be used in a chip, and that simulation will come from your hardware. So basically one simulation will come from the PC, another simulation will come from your FPGA, and all those two will be performed with your PC only. So if your FPGA is not switched on, then hardware simulation will not be performed. So in order to perform hardware and software simulation, your FPGA should be on, and then you can perform both those simulation, and then you can compare the software simulated environment and hardware simulated environment. You can make comparison between these two, and that will be in the form of your actual filter waveform. So basically what here you are going to do, you are going to use gateways, gateway in and gateway out. Gateway in is nothing but it is just like your, as I told you, from MATLAB environment you are getting what, floating kind of input. Gateway in is going to convert this analog input into digital, into number of bits. It is basically is going to convert as ADC, analog to digital conversion. Analog input is coming to your system, we are using gateway in, and that gateway in is the block of your system generator. gateway in is responsible for converting your this input data into number of bits. So if you are using 16 bits, it is going to convert your input into 16 bits in the form of zeros and ones. That will be used by your FPGA. FPGA is nothing, it is going to contain some it is programmed with your bit file after writing VHDL code or Verilog code, and then again it is going to give you the output in 16 bits. Output is again in the form of zeros and ones. So if you want to view the actual waveform of your filter, again you have to use some kind of you can say block that can convert this digital output into analog, right? Then we are going to use their gateway out. That gateway out will be responsible for converting your this digital output, these 16 bits, into analog. So that analog output is going to show you the output of the filter similar to your MATLAB environment, right? If you have developed a low pass filter in MATLAB, you can easily view it from the waveform. That same waveform you will see after gateway out, that low pass filter. So two waveforms will come. One will come from the software, another will come from the hardware, and those two waveforms will be in the form of actual low pass filter, and you can compare these two outputs, and then you can analyze whether the developed system is working as per your requirement, it is showing low pass filter or not. And this kind of simulation is available with system generator, and it is also known as your hardware co-simulation. Hardware co-simulation means you are performing simulation in software and you are performing that simulation in hardware, and now you are comparing them. So this is very important, you can say, feature in system generator, and that feature can be used to perform this hardware co-simulation. Otherwise it is very difficult. You can't perform or you can't analyze the output if it is in the form of zeros and ones. It is going to be just 16 waveforms with 0 and 1 transition, and it is very difficult to analyze whether it is low pass filter or not. It can be done with system generator with hardware co-simulation. So in this way, here you can see that. So complete front-end VLSI design contains, the first thing is, now you need you need HDL code, right? So this HDL code, you have three options. Either you can develop your own code, or you can generate your code by using CoreGen. You can generate your code by using system generator or Accel DSP. Once that code is there with you, the next step is you have to synthesize. So after synthesis, as I told you, two kind of logic optimizations will be performed. One is technology independent, another is technology dependent. So after that, you will get RTL, register transfer level, with complete detail of netlist. So basically now here you have complete, you can say, minimized structure of your complete design. So after this design, three things. In implement design, you have to translate, you have to place and route. This translation also sometimes you call it as mapping. This basically it is nothing but it is mapping. Mapping between you want to map required resource with one of the resources available in the library. So we can say that it is kind of mapping also. We can map, and once mapping is done, then you have to place, then finally you have to route the circuit. Once your complete design is routed, then you have to generate the bit stream. That bit stream will be in the form of what? It will be in the form of zeros and one, as I told you. For example, in our FPGA, if there are 500 bits, and only we want to program 45 out of those 500 bits, only those 45 bits will become 1 and rest bits will become 0, and this bit file is the actual output you will get from the PC, nothing else. So your all programming and other efforts are going to give you this bit file, and this bit file will be used to program the FPGA. So this bit file will be transferred from your PC to FPGA, and like this. So it will be downloaded to FPGA, and your FPGA will be programmed with the help of this bit file. So this is Spartan 3 eFPGA Xilinx, and this program was transferred program was of half adder, and you can see that here these are two inputs are used for giving the input to your circuit. For example, if it is half adder, you need two inputs, X and Y. Likewise, you need two outputs also to verify the circuit. You need one output for sum, another for carry. So for providing actual input from physical devices, we are using here toggle switches. So two toggle switches are used to provide 0 and 1. And by providing this 0 and 1, you have to check sum and carry. So we are using two outputs in the form of LEDs. So we check the transition of those LEDs, whether it is on or off. So as you can see that it is on. So logic is for that one. So in this way, after bit file transfer, you can check your design in hardware by making transition over toggle switches, and you can monitor the outputs in the form of zeros and ones. So this is your complete design flow in the form of you can say front-end VLSI design. Now the next part is our back-end VLSI design. In back-end VLSI design, we have three options. As I told you, different vendors are there, and some of them were Cadence, Synopsys, or Mentor Graphics. Then Microwind is there, Tanner tool is there. So this flow may differ from one vendor to another, because each and every vendor, they try to make their software user friendly. So they sometimes they skip some steps, and they try to make your software easy to use. And designer has the option, you can start with any one of these three you can say options. Actually, in backend VLSI design, mostly we start with schematic, graphical. But again, it depends upon the availability of circuit. If you are working on some circuit and you are following some paper, and if in that paper circuit is in the form of transistors, right, then no doubt you are going to start your design in the form of transistors. If your input data is in the form of gates, then you are going to start your design creation in the form of gates. And sometimes your paper is based on some code. In that case, you have to start with your design on HDL. So whenever we work into these two different areas, front end and back end VLSI design, you always keep in mind, when we go for front end VLSI design, we our end result is bit file, right? End result is bit file. That bit file will be generated, and you have to transfer that bit file to the FPGA or CPLD. If we are working in backend VLSI design, our end result will be layout. Layout is nothing but a number of masks. number of masks you create, that is your CAD part. You create number of masks to create those regions over silicon, right? Silicon area, and then you try to make your own chip in the form of ASIC. So FPGA design means your bit file generation, and your this ASIC design means you are going to create the layouts. So in order to create these layouts, you have different options. You can start from any one of these options, and most important and used input option is schematic design. So your software, they provide two platforms. One is used for schematic entry, another one is used for layout part, means for generation of your masks. So schematic can be entered in the form of transistors, or it can be entered in the form of gates. So your software should be able to support both type of entries, entry in the form of transistors or entry in the form of gates. Again, you should have option at schematic level. You should be able to simulate your design on schematic level, and then you have to move from schematic to layout part, right? So in schematic design, basically you create your design in the form of either transistors. Here you can see on this screen, here one inverter is developed, and it is developed with the help of you can see transistors. Actually, this snapshot is of microwind software, and you will also get exposure of cadence software in this complete STC. We are going to use cadence software because it is industry standard, and it will be more useful for all the participants to start their research. And flow will remain more or less the same. Some provide some kind of additional you can say flexibility in the design. So it is going to be same, and some provide more options so that you can perform more research on your areas. So please don't get confused with these, and these are standard you can say flows. In cadence also you have to again go for schematic, right? So schematic design means graphical entry, and it will be in the form of transistors. Here inverter is designed, and once this inverter is designed, then you have to you should be able to simulate it. First you have to simulate it here. So your software should be able to simulate the design in this environment. So once it is working as per your requirement, then you move ahead with next part. From this schematic design, in backend VLSI design, again you have different options. First option is auto generation, and most of the designers, they go for auto generation. Second is semi-custom design. Third is fully custom design, right? So auto generation means this flow is for auto generation, right? Auto generation means you are using inbuilt transistors, you are using inbuilt layout of transistors, and your software is going to generate layout for you. You are not generating that layout at your own. So here you can say that it is easy. Auto generation is always easy. You can easily generate your layout, and you can simulate it. So again, your simulation will be on schematic as well as on your layout part. So you are you can simulate on both parts. It is easy but less flexible and less optimized, you can say that. Optimization will not be there, and you can say it is difficult to modify. Second option is semi-custom design. In semi-custom design, what we use transistors, internal inbuilt ready-made transistors layouts from the library, but we try to manually route it. We route it from our own side. So routing is from our, we try to optimize the routing part. Fine. So in that case, what we are doing, we are straight away working on layout part. So we have three options: schematic, HDL, layout, and we can work. We can start working from any one of these points, right? So if we are using auto generation, then we can start from HDL. HDL, and it will be converted into schematic, and then from schematic it will be simulated, and you will go till the ASIC. If we are designing some kind of chip, then we can start with schematic. It will be converted into spice file. That spice file will be used to create the layout, and on the layout part we can create use inbuilt transistors, and we are going to use our own manual routing. Third part is your fully custom. In fully custom, you are going to start with scratch. You are not going to use anything from the library. Even you are going to create your own transistors, right? You are not using inbuilt transistors of the library. You are creating your own transistors, and you are making connection between those transistors. That is fully custom. Basically, each and everything you want to optimize. You are optimizing the transistor, you are optimizing the routing part. So it will be optimal in all sense. Semi-custom will be optimal in terms of, you can say, area or speed. You can reduce the area. Fully custom, it will be easy, but it will be less optimal. So again, three options are there. So from schematic, one file will be generated, and this is your spice file, right? How your automatic generation works: you create the schematic, that schematic will be converted into this Verilog file, and this file is known as your DEC file or spice file. This file is basically gives you information about actual physical dimensions of your transistors and other resources used in your design, for which you have to create the layout. So from here you can see that in this design you can see transistor NMOS, PMOS, what is the dimension of transistor, what is the dimensions of PMOS, and along with this it is also giving you different information about their connections, that is netlist. So spice file is basically a file which gives the description of actual physical dimensions of active and passive components on your layout, right? So once this spice file is there, this spice file will be used to create what? To create layout finally. So this layout will be created or auto generated for your particular schematic. So here you can see that three different sections. Either you can start from schematic, you will create its spice file, or then layout, or you can start with HDL. Here in this STC also you will get exposure of ASIC design. We will start with HDL code. We will take that HDL code, we will use it in our Cadence software, and then we will try to create our own chip. So both kind of exposures will be there. You are going to you will get exposure of designing your circuit starting from schematic. You will get the exposure of designing your circuit starting from HDL, and you will go towards the chip designing, right? So if we are using HDL, that HDL will be converted into schematic. RTL, from RTL we are going to create the spice file, and that spice file will be used for layout generation, right? So these two things, you can start from schematic, you can start from HDL, and as I told you, can straight away work on layout part, right? So in that case, you create your own transistors, you create own connections, and then you optimize your design. So three parts are there: your fully custom, semi-custom, and automatic. Right? These three different parts are there, and with this, I end this session, and I thank all of you for be patient in listening this session. Now I invite queries from different nodal centers. Now house is open. You can ask your